Hello, everybody. I'm very happy to see you all. This time I'm going to present a very special speaker because as he holds a lot of wisdom and experience on a very important resource that we have. And we have a scarcity of it, and this is probably a great opportunity. Yes, we can hear you. So this is a great opportunity also to just try to build a new knowledge, I think, of how can we be more sustainable in this very important resource. So we have the pleasure and the honor to have Professor Shane Snyder, world expert in water and ways that the water can be sustainable, and prove that he is the leader of the New Research Center. So thank you very much to be here. We are honored to have you here in the stage. We're going to pass your short bio, of course, and then you can have the floor for you. Thank you, Professor Snyder.
Shane Snyder. He is a professor of civil and environmental engineering and is the executive director of the Nanyang Environment and Water Research Institute in Nanyang Technological University in Singapore. Dr. Snyder's research has focused on water quality, treatment, and sustainability, which resulted in over 300 published manuscripts with nearly 30,000 citations. He serves as the editor-in-chief for the American Chemical Society journal, Environmental Science and Technology Water. He's a fellow of the International Water Association and a board-certified environmental scientist by eminence from the American Academy of Engineers and Scientists. He has served on several U.S. Environmental Protection Agency expert panels. He was awarded the Dr. Pankaj Parekh Research Innovation Award from the Water Research Foundation, the Agilent Thought Leader Award, and the Nanyang Humanitarian Award, among others. Recently, Professor Snyder was awarded the 2021 Clark Prize, broadly considered as one of the most prestigious awards for outstanding achievements in water science and technology. Please welcome Shane Snyder.
Hey, thank you. Thanks. Oh, this is great. I got my fan base here. Huh? Oh. Now, hey, first of all, I want to say I'm so honored to be back here at Tech. This is my third trip, and each time I meet new people to collaborate with, and I think there's a lot of synergy here. And I'm so impressed by the students, the researchers, the faculty, the staff, the administration. So heartfelt thank you to have me here again. So today, I want to go very quickly so that, we keep on time, but share with you a bit about what's going on in Singapore, and it's particularly about this area of water reuse. And the question I want you to all think about: what makes water safe? Could be the WHO, maybe you believe me, maybe not, but what intrinsically has to happen? And what has to happen for us to take our wastewater, the water that we use in our homes, we flush down the toilet, how do we get that water back? And I'll tell you one more thing: whether you like it or not, you will be drinking recycled water, even if you take it from the ocean. I'm going to show you that. So it's not a question of if you will drink it. It's a question of, do you want to control your own destiny or let someone else control it for you? I mean, that's really what it's all about: time and space. So I'm living in Singapore. I've been there for quite some time, for about 12 years. I'm now a permanent resident of the country of Singapore. And it's just an unbelievable place to study water. And I think that the country owes its successes mainly to Lee Kuan Yew, the founding father of Singapore. And this statement he made, I will never forget. This man had to develop a new country. A country that when he started, nobody wanted at the end of World War II. The poorest country of all of Asia, the poorest. And in 50 years, Singapore went from the poorest country of Asia to the richest country of all of Asia. That delta is greater than what happened in China or South Korea, an incredible feat. And when he took over power after World War II, because Malaysia didn't want Singapore, the people were largely addicted to opium, the British took off, the Malaysians said, we don't want this nasty island, it's so bad. So he had to build this country, and what did he say? Water was one of the most important things to build that country. And he did what he said. He made massive investments in education. The fact I got the honor to work in Singapore is largely, I got to meet Lee Kuan Yew just once. And what an incredible statement that he knew to build a country, to build an economy, to have social stability, he had to secure water above all else. Pretty incredible. So what is Singapore today? They went a long way. So over the 50 years, they now have a population approaching 6 million people. It is the highest densely populated country in the entire world and is a very, very small island. It's very tiny, very compact. We have one of the highest GPDs per capita in the world. So again, one of the wealthiest countries in the world. Unfortunately, my salary doesn't show that, so don't expect me to pay the bar tab tonight or something. But what they've done is miraculous. If you go back into the 1970s and you look at Singapore, this is the Singapore River. And on the left side of the screen is what it looked like in 1977. And on the right side of the screen is what it looks like today. He had to transform, the country had to transform a very polluted, a very toxic environment into something of beauty. And by doing that, the companies came. First, Shell Oil was one of the first. Then the banking came, and then more and more and more companies came. And now Asia is the global headquarters of some of the largest multinationals in the world, like Johnson & Johnson, Pfizer, et cetera, et cetera. So water was really important. It was kind of at that foundation to make sure the country could be stable. But again, they started from a really tough place. In the 1960s, Singapore did not have enough water for the people. Now that's hard to imagine because the average rainfall is 2.3 meters per year. Not centimeters, 2.3 meters. You're much taller than me, right? And yet, it all happens during monsoonal rainfall, these torrential flooding, which would actually wipe out, cause fatalities. People lost their homes, their farms. So Singapore had two problems with that. They had part of the year, not enough water, it's dry, where are they going to get their water? And the other half of the year, there's flooding and destroying people's livelihoods. So they really had to do some incredible engineering and science to begin to solve that. So here's what they do. The first thing that they have are pipelines from Malaysia. Okay, now these pipelines have been there a long time. You can still see them today. So this photo is standing actually inside of Singapore looking into Malaysia. Johor Bahru, Malaysia looks like New York City or Singapore now. Massive investments, massive buildings, a lot like what I saw in San Pedro yesterday. Maybe not that grandiose, but very much highly developed. And you know what the Malaysians are saying is, we kind of would like to keep our water. we might need it. Now, I'm going to say, climate change keeps making everything you expect become unexpected. So today, just in the news, just yesterday, there was massive flooding in Singapore and Malaysia. So we're going in these weird cycles. But this was one of the major ways that they brought water. And by the way, the final blow, when basically the British surrendered to the Japanese unconditionally, the Japanese threatened to blow these water pipelines. They said, if you don't surrender within a week, we'll take out the water pipelines and you all die. You won't have enough water. So you can imagine this new leader, why it was heavy in his mind. The next thing that Singapore began to do is they said, hey, look, we got a lot of rain. We just don't got a lot of land. How can we deal with this? How can we capture all this stormwater coming rapidly during monsoon? So this is just one of many of what we call barrages, or loosely you could think of it as a dam. So what are we doing? We're capturing the water from the urban runoff, from the rain, in this catchment, and we're separating it from the ocean. So if there's too much rain, like yesterday, it can allow that fresh water to flow to the ocean. But when there's not enough fresh water, the dam shuts and they keep that fresh water in and they use that for drinking water for the country. Now there's several of these across Singapore. Now some of you may even know this skyline. I was going to bring up something, Probably some of you know who Sergio Perez is, right, from Mexico? He won the Formula One this year, a Mexican driver, and he did so in a very rainy condition. Now, I'm going to come back to that, because what you can see, if you look really carefully, you'll see bleachers and things like that, like a stadium. That's where people watch the Formula One. So I want you to think about this. These cars are racing top speed, their tires are melting and flying off, they have accidents, they spill oil, they spill fuel, they spill coolant, they have all this stuff going on. Where does that water go? Into our drinking water. It's a fact. So no good deed goes unpunished. You want to capture urban runoff, you better think carefully about what's in that urban runoff. And I'm going to end my presentation to speak about that. So what did Singapore also do? And this is how I got involved with Singapore. They started building some of the largest water recycling programs in the planet, at least per capita. And they call it, their branding couldn't have been better, New Water. What a great idea. And the Prime Minister himself endorsed it. The Prime Minister himself drank it. I drank it, on TV in public. Because, if we as scientists and engineers won't drink it, don't ask the public to do that. That's crazy, right? So they made huge investments, and today, Singapore recycles somewhere around 90% of its water. Not just the sewage, not just the wastewater, but also industries. Very strict. If you want to locate a company in the country of Singapore, you must have a water plan. You must demonstrate that you are sustainable, because they just don't have enough water as they continue to try to expand. In the backdrop is ocean desalination. So, okay, Singapore's an island surrounded by the ocean. Surely there must be enough water, right? Oh, sure, if you've got infinite energy. Ocean desalination takes an immense, incredible amount of energy using the very best technologies we have in the world today. And my own institute that I lead, we're funded about $60 million from the country of Singapore. About half of that's for ocean desalination. And I hate to tell you, we are not going to make it energy neutral, energy free. It will not happen. The laws of thermodynamics and mass transfer just limit that. So we make incremental improvement, and that's great. But New Water, recycling our wastewater to ultra high purity water that I would drink, I'd have my kids drink, my parents drink, without a fear, is about 1/5 or less of the energy of ocean desal. That's a driving force for California, for Australia, and even recently we're seeing it in the Middle East. So it's something I want to continue that theme on as I use my time. So, as I said, Singapore's been having this really weird weather. I mean, the whole world's experiencing this, unfortunately. So, from about 2014 to 2019, 5 consecutive years, every year they said, oh, this is a historical drought, never has happened before. But then it happened 5 consecutive years in a row. This is the reservoir that Singapore uses to get its water from Malaysia. So this is 2019, it's about, I think, 16% capacity. It didn't just hit Singapore and southern Malaysia, it hit Kuala Lumpur, right? Kuala Lumpur is a financial center of Asia. Kuala Lumpur had to bring water by truck for millions of people. They ran out of water. And I've never seen that. I can't imagine it, but you go wake up in the morning and you turn the tap and nothing comes out. Luckily, I haven't experienced that, but that is a reality that happened in Kuala Lumpur. It did not happen in Singapore. Why? Same drought, same waterfall. Because Singapore had built the infrastructure in advance. So their reservoirs never fell below 90% during this drought. The ones inside the country. They turned on the water desalination, they kept reusing their water, and they were able to survive that. And today, Singapore could survive without the water from Malaysia. It's just more energy intensive. So, like I said, it's not just drought. All my career I talk about drought. Well, what about when the weather changes and all of a sudden there's flooding? And you just built billions of dollars of ocean desal facilities. First of all, 1 year of rainfall is not ending a drought. And I had to say that to governments around the world, my own home government in the States and Singapore, build the infrastructure because you don't know what's going to happen. So Today, Singapore has had massive flooding for the last 3 years. We got over 3 meters of rain last year, more water than we can figure out what to do with it. But that also creates unique water challenges. Remember I talked about that stuff that runs off the roadway, the Formula One race? What about the photo on the right? This is Singapore last year, right? Flooding, the cars. Imagine all that stuff from the cars and the oil and the tires and trash and all these things that you don't really want to drink being washed into your drinking water reservoir because you are capturing it by intent. So also anything that's spilled. If you spill something in Singapore on the road or in the canals, it could and likely will end up back in your drinking water. So they have massive programs. There's so much opportunity for students and for faculty, even for collaborations here with Monterey Tech, to look at new sensor systems. We need to detect this before we find out it's in the water, which is exactly what happened a couple years back when the water started to smell weird. It smelled like pandan. This actually smells nice, but you don't want your water to smell like perfume, right? You know something's not correct. And that chemical spill happened in Malaysia, and they didn't detect it until it was too late. So there is a massive future for machine learning and different AI systems and sensors to feed that data. Without the data, you can't really build the system. But I want to speak at least briefly about the area around Singapore. We're this tiny little island, right? Some people say, hey, you're inconsequential, you're just small. But around us is Southeast Asia. We have 650 million people. Before the pandemic, the most vibrant economies in the entire world, and Vietnam and Thailand just growing and growing and growing. A lot of movement of industries around from China, different places, and I know Mexico's experiencing that too. So it's hard though, and I feel bad when I think about my neighbors just across the bridge, that we have about 140 million people that don't have safe drinking water in Southeast Asia. Then we think about sanitation, well then it's even worse, right? The whole Asia-Pacific region, up to 80% of the population does not have sanitation. That causes massive detrimental effects to the environment. It contaminates the drinking water, and it has a lot of deleterious effects to the whole ecosystem. So there's a lot of work to do, but as researchers, there's so much opportunity. We must be finding new ways to do cost-efficient, sustainable technologies that can be deployed to the people that need them the most, not just the richest countries like Singapore, but how do we get them into other countries that are still developing? Now, Southeast Asia, just another quick point. Unfortunately for us, it is considered the most prone to damages from climate change. We're at the equator, we're 1 degree off the equator. So as the oceans begin to rise, that impact will be felt mostly around the equator. So Southeast Asia has been predicted to be one of the worst. And if you want to see Bangkok, which I strongly recommend, wonderfully beautiful, one of the top tourist cities in the world, well, you better hurry up, because it might be underwater within 15 years. Now, is that sea level rise? Yeah, in part. But it's also because they pump too much groundwater. That whole city, it's a massive city. I think they don't even know the full population. Was pumping groundwater, pumping groundwater, pumping groundwater. And the city started to sink. And now as it's sinking, sea level rise is coming up, and what else is happening? Storms like we have never seen before, ocean surges, tsunamis. So Bangkok is in peril, and the Thai government is well aware of it, and they're making investments to try to abate it. Now, one last comment. Once your city subsides, you can't bring it back up. I mean, you can't bring it back up by pumping water in the ground, but what you can do is you can stabilize it. So some of these damages can't be fixed. Another example from Hanoi in Vietnam, they're seeing tremendous subsidence and potholes or sinkholes because the aquifer is gone. But the biggest and most incredible is Jakarta. And Jakarta is about a 45-minute flight from Singapore, the capital of Indonesia. You know, the Indonesian population is 285 million people. It's similar to the US. And yet, their capital city is gone. It cannot be fixed. So they are moving. The entire capital of the country of Indonesia is now relocating because they've just given up. Jakarta likely cannot be fixed because they pumped too much groundwater, the city sank, the ocean's coming up, and they're losing their land. But there's also thinking about food supply. This one was, again, is 2015, and a lot of the production of rice in Southeast Asia had moved to Thailand. Massive agricultural activities, a lot of money being made, and then boom, it stopped raining, and the rice supply for Asia, which is a staple food, was in peril. People were scared. Where are we going to get our rice? Where are we going to get our staple food for about half the world's population? So these things are real. They really happen. Now, as I was putting this together, I kept hearing about the droughts here in Monterrey, and I'm going to show you America as well. And I saw this from the New York Times. I guess this was last summer. So I think the folks here, you guys are uniquely aware that this can happen and that it is very detrimental and very much at risk. But again, there's good news. I see you're telling all this bad news, you know, but that's what we're here for. We as researchers and students for jobs of the future, we have a responsibility to our homeland, to our countries, to help. And again, the United States is a disaster. I used to live in Las Vegas, Nevada, then in Arizona. In Arizona, we are shutting down entire, I won't say cities, but towns that don't have water rights. The governor just said, okay, forget it. Your town is gone. Your land is useless. Financially crippling. So I'm trying to sell my house in Arizona if anyone wants to buy, because I'm a little bit nervous about the water. But it is a real phenomenon, and this began around 2000, 22 years ago. And this year, just yesterday, last night, it's snowing in California. Okay, that's great. But we can't give up, because 22 consecutive years of drought, even if this year is good, it won't fix the problem. And I just want to mention this, because this is another just interesting one. I think in the US, this is really becoming a big issue now. I've seen it in Australia, and actually in Thailand, too, where they want to preserve the ocean's clarity, a lot of recreation, beautiful beaches, etc. And yet, a lot of us in California, Florida, we put our waste back into the ocean. There's two problems. We add nutrients, we cause pollution, we cause algae, we lose those beautiful blue waters, become green. But the other side of it is we're losing water. You know, that water is fresh water. We can recycle that, reuse it at low energy back into the cities. And that is exactly what Singapore and Los Angeles and Perth, Australia are beginning to do more and more. All right, so with my remaining time, we'll talk some science, huh? So I am an advocate. I believe firmly that potable water reuse, taking our wastewater to drinking water, is safe, it's sustainable, and it's not really drought prone. I guess if you have no water, you can't recycle it. But assuming you have water, you can recycle it safely. I'm a member of the World Health Organization. We had a 2017 document. You can read about it, what our expert panel determined. Same with the National Academies of Sciences. I was also part of this panel for the United States Congress. But I wasn't part of this panel. Okay, I'm not that old, right? I know I'm old, but come on, give me some credit. But even as far back as 1975, the WHO said, hey, this is safe. So I think it's more social science here than it is actual risk to health. But why are we worried? Well, it sounds yucky, right? We've associated how much disease with contamination from sewage into drinking water, back with John Snow, originally in England with cholera. So we think, hey, if we got wastewater or sewage, we better stay as far away from that as we can. And I don't have time to tell the story today, but remember I said I was working in Las Vegas, the city of Las Vegas, for a decade. And this is what we were fighting. Now, an interesting thing, if you look at the center photo, they're showing all these drugs and pharmaceuticals and steroids. The public, ironically, is seemingly most concerned about the chemical contaminants. Right? As a scientist, I'm more worried about the pathogens. One glass and I might die. And that almost happened to me in the Philippines about 2 weeks ago. Some of you know that. So I learned the hard way. You've got to be careful. But the stuff that I'm going to talk about for my remaining time is more chronic. If you're drinking it all the time, if every day you're getting low doses of chemicals, what happens? And the problem is so daunting because there are an infinite number of chemicals, whether they're natural, synthetic, nanoparticles, microplastics, whatever, anything you can dream of. If we wear it, if it's in our room, it's in our water at some concentration. And we have to give up doing chemical by chemical by chemical. We cannot. The WHO, which I have served on, we come up with a few standards every 5 years. We build more chemicals in one day than the WHO could address in a decade. So we have to think outside the box, and that's what I want to leave you with. So for the state of California, they've been some of the most avant-garde in terms of being proactive around water recycling because they have to. You know, when the drought began to hit San Diego, some of the biggest pharmaceutical companies in the world said, hey, we're leaving San Diego. I got called in, I got to meet with the mayor. They were saying, hey, you know, we can't lose the biotech industry or our economy is going to collapse. So California is now like leading the world, I think, in water recycling. So the question came to the scientific panel, how do we ensure safety? First and foremost, sensor technology. If something goes wrong, you want to know it before people drink it. You don't want to have to tell the public, hey, wait a minute, I wish you hadn't drank that yesterday. You know, that's bad messaging and people lose their political careers over it. So, and I know here at Tech Monterrey, there's a lot of people working in this. This space is wide open. And for you entrepreneurs, if you've got a new sensor algorithm, I can help you sell it in Singapore. I don't take commission. But I know the Singapore government will immediately buy it because they are trying everything to monitor the sewer because it becomes the drinking water and they don't want surprises. Second, I call it indicators. You cannot measure every chemical in sewage. You can't do it. Or even if you could, it would be impractical, implausible. So you can pick certain chemical markers based on their physical chemical parameters. And you can make a lot of data, a lot of decisions on a small amount of measurement. But the part that I'm passionate about my whole career has been this tier 3. Now this is more complicated. And I am probably one of the world's largest advocates for in vitro toxicology. Now I will admit that in time it's going to be in silico, but maybe I'm too old for that. But in vitro, and the US EPA has announced they are banning animal testing by 2035. Well, so if we can't do animal testing, I think in vitro is our next line of defense, and it's faster. And by the way, giving a mouse or a rat or a rabbit a chemical and watching what happens, that doesn't represent the human body anyway. And we could talk about that over coffee or beer later. It's kind of interesting. So let me just show you an example. Indicators and surrogates. So I'm going to just go quickly. If you like this work, if you're some kind of science person, a nerd or whatever, I'll talk later. And we publish most of this work. This is just showing secondary wastewater treatment. This is like the most prime barrier against pathogens and chemicals. But we can't possibly measure all these pharmaceuticals and hormones. So what I'm saying is, look, there are two major pathways. Absorption, it binds to the biosolids, or it biodegrades. There's other things, volatilization, et cetera. But if we look at things that don't biodegrade, that tend to absorb to the biosolids, we begin to see the things that are most common in the water. And so we can measure them. So if I take a water sample and I see those chemicals in a red box, I know that I know there's wastewater somewhere. If I see the ones on the opposite diagonal, triclosan and fluoxetine, one's an antimicrobial, one's a pharmaceutical, I know that there's no sewage treatment, or it's not working properly because they should not be there at appreciable detection limits. And now we can apply this, I won't get deep into this, we can apply it to ozone, one of the best disinfectants known to humankind. We can begin to say, okay, if it can destroy these types of chemicals, we can then build a molecular model that can predict. And I'll show you, we can do it in real time. We've done it also for UV, advanced oxidation, when you take high energy ultraviolet and add hydrogen peroxide. Same idea, we can do certain indicators, we don't have to measure everything. And we can use surrogates like fluorescence. Fluorescence is my favorite. That's the kind of beautiful looking, if you will, boxes, but you can see changes as you change the UV dose or the peroxide chemical. And with ozone, again, we published this work. We built beautiful models that can use online ultraviolet or online fluorescence, which is a little bit more novel, and we're working on it. But we can put this into a computer system and monitor the change in this fluorescence, and we can predict how well it'll disinfect viruses, cryptosporidium, and in this case, different chemical contaminants or emerging contaminants, if you will. So what about this non-targeted? So this is where it gets more fun for me. This is what happens when we ozonate or recycle water. Now, I don't want to go deep into this, but if you look at these 5 chromatograms, the raw water and then 4 ozone doses, to the naked eye, when I was a student, I'd look at something like that, and maybe I see one unique peak, and I'd be like, hey, what's that? And that's interesting. But behind these chromatograms are thousands and thousands and thousands of data points. And when you apply statistical power to this, like I use molecular profiler professional mainly, which is a type of PCA, we see that these waters are statistically very different. And then we can even go deeper and start doing a heat map. And what we see is that as we add ozone, we destroy, if you will, certain compounds, but at the same time we make new compounds. And where I'm always interested scientifically is, did we make the water safer, or did we actually make it less safe? And I'm going to scare you at the end with an example where we made it maybe less safe. So just one example. This is called benzotriazole. Benzotriazole is a very common anti-corrosion agent. It is ubiquitous in wastewater, from laundry detergent predominantly. So we add ozone. In my first paper, we said, oh, it disappeared. Now, a scientist shouldn't use the word disappear, right? Like, that's magic. And unfortunately, I'm incapable of magic. So what happens is it didn't really disappear. It became something different. And the big question for all of you to think about, well, which of these two would you rather drink? Now, of course, you'd say none, right? But you don't have that choice. The point is, we are forming a different chemical. And that different chemical, is it toxic or not? Well, give the WHO 5 years, give the US EPA 20 years, maybe they'll tell you, right? And it's too late. So we need to be faster. Another example, carbamazepine is a very interesting pharmaceutical, and we see it, I've seen it in every wastewater I've ever looked at in the entire planet. And again, we add a small dose of ozone, we see the carbamazepine drop, that's good, but then we see this new peak starting to come up, and what we discovered and published was that it's a compound called BQM, which is actually known to be toxic. In other words, we made it more toxic by ozonating. So we have to be careful of this. And in the final minutes, I'll share with you, I think, a pretty neat story. This is the newest work from my research group. And I'm sure all of you have heard about the microplastics and a very big fear of plastic. Some of it's probably overdrawn, to be honest. And we started by doing a study with UC Riverside and a group in China, where our lab was looking at things that we found ingested in seabirds. So the seabirds and fish are eating these plastics, they're in their stomach, but what happens then? What do these chemicals are released or leached, and what do they do? So I'm not going to talk about that one, I'm going to jump to this one. Remember we were talking about Formula One, which I like, and motorcycle racing? It uses a lot of tires, right? Even my own car, I feel like I'm constantly buying new tires, right? Where do they go? They don't just magically disappear, right? They've become to shred particles, and those particles are microplastics or polymers. And one of my friends, I was so jealous, published this paper in Science. And I read it, and I thought, wow, this is the best work I've seen in a long time. He demonstrated that these compounds are actually formed when the tires get hot. They oxidize, and these vulcanization chemicals get into the water and are extremely, extremely toxic to fish, particularly salmonids. And I know, I met a lot of people here in sustainable manufacturing, huge opportunity to find replacement chemicals for vulcanization. And I actually know a couple tire companies that will hire you today if you want to talk to them, because this is not my field. But again, just an example of green chemistry that could be applied. So what happened? I need to wrap up the story. So one of these chemicals that was detected, I'm going to call it DPG. And DPG has been found all over the world now. It's in water supplies. I can't show you the numbers for Singapore. I might go to prison, but I can tell you that it's there, right? You know, of course it's there. We capture this urban runoff. Now, to humans, at first, everyone said, okay, DPG does not appear to be very toxic to humans. We said, that's really good news. But what happens when we put it through the water treatment plant? And shockingly, very shockingly to me, it became several different halogenated byproducts. So as we added chlorination, pinnacle for water safety, we began to halogenate these molecules in different ways. So first of all, we developed a very high-speed analytical method. That's something today's technologies allow you to do. So we could quantify it, we could measure how much of it was there. But where it gets exciting is we wanted to say, does it matter to human health? And I don't have primates and I don't have mice and rats in my lab, but I have almost every imaginable human cell. So I'm going to quickly just show you now in conclusion what we found. So this is cytotoxicity. This is old school. So we take liver cells called HepG2 cells, and we use human lung cells because we also inhale these particles. And what we found was that some of these chlorinated byproducts were indeed more cytotoxic than the chemical it started with. But this is where the story gets interesting for the state of the science. So here we have these two things, we'll call them CC11 and CCO4, these byproducts, and yes, they're a bit more toxic. But using very modern technology, stuff I didn't have when I was a student, only recently acquired, we can actually look at the cell's health over time. This is called real-time cell analysis. And we can also look at their mitochondrial, or what we call bioenergetics. And so many different endpoints, I just don't have time to go through them. But now, we start to see a whole different pattern. We realize that if we give the cells time, these chlorinated products are often far more toxic than the parent compound. So we see this much more dramatically, much more statistically significant. We also now have tools to do full-blown human genome, right? So we can do transcriptomics, we call it. In this case, my group, we were measuring about 25% of the human genome, so not the whole genome, but a lot of it. And what we see in this volcano plot and in the Venn diagram are that the chlorinated products were different than the parent compound. And what really gets exciting, if not scary, is you can plug that data now into molecular modeling or computer algorithms, and it can tell you, what does this mean? You've got thousands and thousands of up and down regulated genes. We also have the metabolomics, which I don't even show. But what we can do is begin to group these. We can say, look, if all these certain genes in the human genome are upregulated, it could mean cancer. It could mean diabetes. It could mean different things within that human genome because it's looking at similarly up and down regulated genomics. So what we're showing is that these two chlorinated byproducts have a very significant propensity for cancer. They inhibit the cell's ability to repair its own DNA. It's causing double-stranded breaks and really a lot of damage into the genome. And for one tire company I won't mention, a good group of folks, that was, they thought, well, that's a little too heavy. We can't get our mind around it. So I said, well, how about this? This is the human cells, and I'm showing you in photography the double-stranded break of the DNA. So this is a overt genotoxicity endpoint from the chlorinated byproduct. So they were more compelled by that kind of data. And lastly, just to mention, I don't have time to get deep, zebrafish embryos are also incredible, what we can do in metabolomics and developmental, because a lot of the chemicals we're exposed to, we are most susceptible as a fetus and during early development. I wish I had time, but I'm out of time. But anyway, something that we're working on, we'd love to collaborate with. So the path forward, I rushed through this, but there is incredible opportunities for the students, for the faculty, for scientists, for people that are leaders in the governments to be thinking more holistically about water and water recycling. We can't afford to just dump our water out in the desert like we did when I was in Nevada or in Phoenix. And we can't put it back in the ocean because then we can't get it back very easily. But to make sure it's safe is critical. We don't want people to take a risk and have them develop cancer. We find out from our epidemiology friends, like the previous speech. So I see this path forward of sensor technology. Is the system working or not? If not, shut it down. Indicators. Let's use a few things to monitor the system. And lastly, and I think most importantly, rapid toxicological screening, which doesn't do just one compound, but all of them simultaneously. And I'll leave you with just a heartwarming final slide. We can take that same work path and we can turn it upside down. And my student who's next to me, Mauricius dos Santos, is the most brilliant student I've ever had. I shouldn't say X, I have a lot of students. But he discovered a potential cure for asthma based on natural products. People are like, how does that relate to water and on these tires? It doesn't, but the workflow is identical. a company that wants to develop a new pharmaceutical or a water agency that wants to look for toxicity, that workflow is essentially the same. So again, I want to acknowledge people that really do the work. You know, I'm lucky to come to Mexico and meet my friends again and have a great time. But back in the lab, the people who do the real work are working hard, and I appreciate that. And I thank you for your time. I hope I didn't go over too much. But I'm always happy to talk to people, particularly our students, faculty. So feel free to drop me an email. If I don't answer, write again, because I lose track. All right? All right, thank you so much. Okay, thank you.
Thank you very much.
Yeah, thanks for being
Yes, just, I don't know, I think we are very short of time for questions. I don't know if you have a question, somebody. It's a very interesting challenge that we are facing. This is basically for humanity. Let me.
Hi, Professor. Thank you so much for your talk. You know, I'm part of your fans club in Mexico.
Oh, thank you.
In Mexico, recently, we have a new policy that make all the water discharge to verify toxicity in water. And something real interesting about the transformation subproducts after the treatment is the new development about nitrogen contamination in water and groundwater is identify the water treatment process has the source of this contamination. I saw already that you have like some of the big points, like online monitor has the big giants, but how can we develop this technology for all the water dischargers? Because sometimes it's real expensive. In my opinion, I work with MIT in development of sensors for nitrogen, and the sensor costs about $10,000. So
Yeah.
it's too much.
Right.
And what is your opinion?
Karina, that's a really, really good question, because sometimes I show these data and I don't admit that, you know, some of this QTOF technology is super expensive and it's complicated. But I want to break it down. Just really, I need to answer it quickly because I want to move on, let other people have time. But, you know, your point's exactly right. We need to be able to do this at a cost point that can be applied to the people who need it the most. The people within Singapore, I don't think they're drinking dangerous water. But I just go to the Philippines and I almost died, right? You know, it's so dramatic. So I wish I had a little sensor. I would have probably saved some hospital time. So I just would say, I'll leave it at that, to say it's very, very important to develop low-cost, high-speed, pathogen, and to a lesser extent, chemical detectors. But one last quick comment. The in vitro technology is actually inexpensive compared to the mass spectrometry and even compared to some of the sensors. That in vitro platform is not super expensive. I know it's all relative, but I think your question's great. We really need like very rapid, immediate tests for water safety. That's a human right that we should be looking for a global solution. So good point.
Thank you, Karina. Somebody else has a question? Doctora Rocio Ortiz, please. Only one question, sorry. Go on.
Thank you. It was a great talk. And I have a question I don't know if in the process of treatment of these waters, what about the pathogens? You already know that is my interest, but do we eliminate the pathogens with this treatment?
Yeah.
Or I am scared to drink that water, you know.
So again, what a great question. Absolutely, pathogens are more important than everything I spoke about. I would urge people, don't stop using chlorine because you're afraid of the byproduct. But also, as you know, and you're an expert, pathogen monitoring has went a long way. And even for our lab, before COVID, we hardly did anything, and now we can do all kinds of genomics. And I know you're working as an expert in ways to do that quicker. So I think that is absolutely the most pinnacle of water safety is pathogen. One time and you could die. I don't think chemicals, that's going to happen unless something really went awry. But your point's well taken, and I look forward to collaborating on that.
Excellent, Doctora. Thank you very much. I don't think we have more time, but we wanted to give a token of our appreciation, really enlightening talk
Thanks,
to
Arturo.
Dr. Molina, our
you.
director of the Institute.
Thank you.
Thank you.
Journalists want to interview.
They wanted to